So now we're going to introduce the concept of the mole. And the mole is often described as the chemist's counting unit. So, like many disciplines have a specific counting unit. So, for example, wheat is sold by the bushel. And the reason being is, who wants to buy individual grains of wheat, right? It's too small. So bags of wheat, called bushels, is a much more convenient counting unit. If I'm buying paper, I don't buy individual sheets of paper because that would be inconvenient. Instead, I buy reams of paper, and every ream of paper contains the same amount. If I'm buying bread, I don't buy individual slices of bread. I'm going to buy a loaf of bread. So different disciplines have different counting units, and the main reason for having these different counting units is to have a reasonable number of the unit of interest. So for chemists, counting individual atoms and individual molecules is kind of a little ridiculous. Instead, what we're going to be doing is using this counting unit called the mole. So it's kind of like a dozen, if you will. That's another definition. People often call it the chemist's dozen. All right. So it's like a dozen. It's just a convenient number of things that gives us a reasonable number. So in the chemistry lab, the most convenient way to measure the amount of a substance is by weighing, right? So measuring things in amounts that are like somewhere between about we have 2 decimal point balances, about 0.01 grams up to maybe about like 1,000 grams. That's kind of like, they're like really convenient amounts of things. The difficulty that we have is that atoms and molecules typically have masses that are a lot smaller than the amounts that are convenient to weigh. So the question is how can we use the convenience of weighing and then somehow relate that to the number of particles, the number of molecules, the number of atoms that are present, right? So that's the kind of the challenge that chemists have. It's easy to weigh something. It's hard to count atoms and molecules. How do we relate the two? So chemists developed a system that allows us to use practical amounts of mass to count the number of atoms and molecules that are present. This is called the concept of the mole. And the mole is a pretty simple idea. It is the number of carbon-12 atoms in 12 grams. So basically what we're saying is that one carbon-12 atom we know has a mass of 12 AMU, but 1 mole of carbon-12 atoms has a mass of 12 grams. Exactly, right? Because it's easy to weigh out 12 grams. It's very, very hard to count out individual atoms. So someone did the activity once. How many carbon-12 atoms are in 12 grams? And it turns out that it's this number. 6.022 by 10 to the 23 carbon-12 atoms. So that is the mole of anything in 1 mole of a substance. Just like 12 is the number of anything in 1 dozen, right? And this number has a special name. It's called Avogadro's number. And here it is with its units written in 6.022 by 10 to the 23 objects per mole. Now for chemists, the objects are normally molecules, atoms, ions, or electrons. But you could have a mole of anything, right? And we do problems like imagine you had a mole of pennies, or imagine you had a mole of donuts, or something like that. We will do problems like that. It's just like saying you have a dozen of something, and you can have a dozen of anything, just like you can have a mole of anything. All right. Sometimes instead of saying objects, chemists will say particle, but it means the same thing. Okay, so Avogadro's number can be rearranged to give 2 conversion factors. They're both the same though, right? 6.02 by 10 to the 23 objects in 1 mole, or 1 mole in 6.02 by 10 to the 23 objects. One will turn moles into objects, the other one will turn objects into moles. All right. So what we're really saying is Avogadro's number can allow you to convert between moles and number of objects. So here's a good question. How many moles of donuts are there in a 24 box? Now I know it's not going to be very many because you need 6.022 by 10 to the 23 donuts to get 1 mole. So it's going to be a lot less than 1 mole. So I need something to allow me to convert from my donut, which is my object in this case, right, into moles. So here's Avogadro's number, and I want to go from objects into moles. So what that means is my conversion factor, which is going to be one of these two guys, must have objects on the bottom and moles on top. So it's going to be that one, right? So objects per mole, and there you go. I get a tiny, tiny number of moles. Not very surprising, because like I said, you need 6.022 by 10 to the 23 donuts to get 1 mole, and we've only got 24. So where this gets really kind of helpful is when we look at the formula of a compound, and we were doing this before in terms of like atom ratios, we can use the subscripts now to create these things called mole ratios, right? So instead of saying that in this compound we have 2 atoms of nitrogen for every 1 molecule of N2O4, we can now say that we have 2 moles of nitrogen atoms for every 1 mole of N2O4 molecules, right? And of course we could write the conversion factor equally validly up the other way. Similarly for oxygen, instead of saying that we have 4 oxygen atoms for every 1 molecule of N2O4, we will now say that we have 4 moles of oxygen atoms for every 1 mole of N2O4 molecules. Or again, if we wanted to convert something else, we could do it the other way up. So we now can establish what we call mole ratios instead of just like atoms to molecule ratios. And we can do all the same things that we were doing before we knew about the concept of moles. So again, here I go. I've got 1.5 moles of caffeine. How many moles of carbon atoms, hydrogen atoms, and nitrogen atoms, and oxygen atoms are there? It's exactly the same as before, but instead of dealing with individual molecules and individual atoms, we're now dealing with moles of molecules and moles of atoms, okay? So moles give us more reasonable amounts in terms of the number of grams that are present than if we were talking about 1 individual atom or 1 individual molecule. Just like it's inconvenient to talk about an individual grain of wheat, okay? Otherwise, the process is exactly the same. We use our coefficients to generate our conversion factors, and we always make sure that we have what we want to cancel on the bottom line of our conversion factor and what we want to keep on the top line of our conversion factor. And you see that all the way through. So always write in your units and always make sure to cancel them. There's no point in writing them in if you don't cancel them. And then double check that you really do have only the units you want in your answer. And you can see I've got that every time here. Moles of nitrogen atoms, moles of hydrogen atoms, moles of carbon atoms, moles of oxygen atom. That's exactly what I wanted in my answer. Again, we can apply these in the same way that we were just talking about like whole atoms or whole molecules. We can now talk about moles when it comes to a chemical equation. The coefficients here in our chemical equation are giving us our mole ratios. So instead of doing like atoms of A to atoms of B, we're now doing moles of A to moles of B. So if I wanted to calculate, it says here, if 3 moles of iron is reacted with oxygen, how much Fe2O3 is produced? What am I going to do? 3 moles of iron, and I need to turn it into moles of Fe2O3. So I'm going to create a mole ratio using these coefficients. You can see here I get 2 moles of Fe2O3 for every 4 moles of iron. So moles of iron cancel out, leaves me with the units that I need in my answer. And these numbers here are just my coefficients, right? Okay. So it's a pretty simple idea, and it's why we hammer you kind of like week after week on using conversion factors, because we're just going to use them again and again and again and again. Okay, so how does it work? Well, we're doing a moles of A to moles of B conversion, and what we're going to use to do that conversion is a conversion factor known as the mole ratio. How do we get the mole ratio? We're using the coefficients of the things that we're trying to interconvert between. So these are either going to be the numbers that appear in front of the formula in a chemical equation, or they're going to be the subscripts in a chemical formula. Okay, so that concludes this video where we introduce the concept of the mole. We're going to keep working with the mole throughout chapter 6, so it's really important that you get a firm understanding of this content.